Good afternoon, everyone. Welcome. My name is Diana Wall, and I am the director of the School of Global Environmental Sustainability. And we welcome you all to another one of our lectures that we have throughout the year to have one of the experts. In this case, we've got Rob Jackson, who is an ecologist, has been working on ecology and climate change for a number of years. Rob got his PhD at Utah State University. He did a postdoc at Stanford, and then he was at Duke University for a long time. At the Nicholas School of the Environment, most recently went to Stanford University. He's a fellow of AGU. He's a fellow of the Ecological Society of America. And what has been fascinating, particularly knowing Rob, and many of us do who are ecologists, it's been the different systems that he has worked on and the different perspectives he brings to both energy and the environment to give us a more holistic picture of what's happening in our world. So it's with great pleasure that I introduce Rob Jackson. Rob? I was supposed to say, I'm getting a signal here, that at the end of this, we will stop him, and we also have cards if you don't have any, or if you have lots of questions and you want to pass those cards to the center, and we'll pick them up, and then we'll try to get as many questions and answers in as we can in the short time that he's here. And I should say that Rob has very graciously come here from a big meeting, American Chemical Society in Denver, and he's been on the road doing both research and meetings like this and giving talks like he did in Denver. And so we really appreciate him taking out the time when he could be on a plane home to see his family. Ron.
Whoa. Can we turn the sound down? How's that? Is that all right? Well, it's a pleasure to be here. Thank you, Diana. Thank you all for being here. So it's true. I had in graduate school, I studied ecology, environmental sciences, and statistics, but I did have this previous life as a chemical engineer as an undergraduate, and my first job was with the Dow Chemical Company. And so in some sense, this work with energy kind of brings some of that knowledge and history back full circle with the environmental sciences that I do now. So that's somewhat the perspective that I have on this issue in addition to traditional ecology. So our topic today is the environmental footprint of unconventional natural gas and oil, something you're all well familiar with here in the Front Range of Colorado. The photo is a photo I took from the Marcellus. I was up in a helicopter looking down on a well pad operation. And you see the intensity of that operation. You see the generators, and you see water tanks and lots of other things. And then you see that house in the background up here. And I guess I just want you to think about how your view of that operation, this is temporary, of course. This is not permanent like this. But just imagine how your view of that operation might change depending on whether you own the mineral rights to that operation next to you, whether your neighbor owned the mineral rights and put the well pads as close to your property edge as they could, whether your mineral rights were severed 50 or 75 years ago and people didn't even know, the owners of the surface rights didn't even know that until someone knocked on their door and said there's going to be an oil and gas well drilled on your land. So all of those things you see in places like the Marcellus and replicated many other places around the country. And I think it's one of the reasons why this topic can be so controversial. And in our field work in Pennsylvania, in Texas, in Arkansas, I meet all kinds of people who are really happy, dairy farmers in Pennsylvania who are grateful for the royalties that they've received, being able to buy new equipment and such. And I meet people who are bitterly unhappy with how things have gone for them. And part of my interest as an environmental scientist is how to sort of nudge that spectrum more towards the positive side of the outcome. So the spirit of the talk tonight will be, what kinds of data do we have? How do we know what we know about different risks? But also then, how can we make a positive difference for some of these? Okay, diverse views, to put it mildly. That Time magazine cover was, I don't know, 3, 4, maybe even 5 years old now, but was really one of the first very public discussions of this issue and brought up the potential, the magnitude of this resource for both oil and natural gas. A cartoon in the bottom, and then the photo in the upper right is one I took in the Marcellus with the drilling rig behind the house, and I picked that one because that was a particular case where father and son were no longer talking to each other, because father and son were in sort of opposite ends of that spectrum again. So anyway, diverse views I think is an understatement. All right, hydraulic fracturing is here to stay. So as an environmental scientist, in our community, it's part of my effort, my interest to ask how can we improve the environmental footprint of all operations and all the ways we generate our energy. It's here to stay. There's a lot of it around the world. And its environmental footprint depends in part on what fuel it replaces. So you never hear me talk about whether something like unconventional oil and gas extraction is good or bad. It's always just good or bad relative to something else. And we'll talk about some of those metrics. And that something else might be coal in some circumstances, might be nuclear, might be hydro, might be other renewables, might be biofuels. And it might be greenhouse gases or air quality or water, depending on what metric is of interest then. So that's sort of the spirit that we'll look at tonight. The meeting in Pittsburgh that Diana mentioned that I just returned from last week was an international meeting on oil and gas and had people from all over the world, China, Argentina, 3 or 4 European countries, South Africa, and each country sort of thinking about what they're going to do, some moving very slowly. England being an example, the UK being an example of a country that's moving ahead very slowly, not likely to be a major part of their energy mix, but very likely to have some hydraulic fracturing and horizontal drilling there. France and Bulgaria have bans. You've got the fascinating interaction in Poland, almost completely reliant on Russian natural gas, and yet they're pulling back from their potential exploration, in part because of geological difficulties, in part because of other factors too. And then you've got the two countries who, in my opinion, are the most likely to forge ahead quickly. Those two countries are China and Argentina. China, because of obvious air quality issues that we'll talk about a bit more, and Argentina has a long history of oil and gas extraction. They've already drilled a couple hundred exploratory wells, and they're likely to move ahead very quickly. And then China is moving ahead quickly with everything, so renewables and everything else. Okay, I'm an environmental scientist. What are people concerned about? This is a partial list. Land disturbance issues for the ecological community. What is the footprint of the well pads, the roads that connect those operations, the pipelines that are put in the ground. And that's not so different really than something like wind power. Not necessarily the same in terms of area, but for winds you have roads, you have pads that have to be put in place to hold the turbines and things like that. So there are many people working on land disturbance issues and the footprint. There's some good things going on there. The well pads now tend to be larger, but they also tend to have no longer one well per pad, but perhaps a dozen wells per pad. So bigger, more intensive, but much fewer of them, if you will, which is good. All right, so land disturbance. I won't talk about that tonight. I will talk about water quite a bit in 3 areas. The water that's required for hydraulic fracturing and how we place that water use in the context of other fuels. Drinking water quality, something I and my colleagues have worked on, and I'll try and remember people as we go along. Disposal of produced waters, what to do with that 1 trillion gallons of wastewater that we generate in this country from oil and gas operations. And it's fair to say that our oil and gas producers produce more water, wastewater, than they do oil and gas. So there's a lot of this, and it's in general pretty nasty quality, and we have to keep track of that water, keep it from out of our surface waters. So that's sort of the water component. I'll have a shorter component on air issues with some Colorado examples. And then I won't talk about earthquakes from hydraulic fracturing and disposal, but this is, I'm not a seismologist, but this is primarily an issue on the wastewater disposal side, not for hydraulic fracturing itself. What to do in many states, about 90% or more of the wastewater generated in the US is pumped back deep underground. And it doesn't matter whether it's water for hydraulic fracturing or carbon dioxide capture and storage, or even some aspects of other wastewater disposal or geothermal. Anytime you pump a lot of fluid underground under very high pressure, you can cause rocks to slip against each other. So there's a lot of work going on in the induced seismicity area, and places like Oklahoma have been in the news very much. They had more earthquakes in Oklahoma last year than my home state of California, which is completely new. All right, let's talk about water for a bit then. There are some good things going on in the waterfront. We'll start with those. In Pennsylvania in particular, the state is reusing about 90% of the wastewater generated now. So that means when that produced water, that flowback water, comes out of the ground, instead of being disposed, it's typically treated a bit and then brought to another well, mixed with fresh water, and then used to hydraulically fracture the next well. Maybe typically 15 or 20% of the total water use, because you don't get that much of it back out of the ground. But that change is good because it obviously reduces the amount of fresh water that you need, and it also reduces the amount of wastewater to be disposed of. Now, that's not happening in other states, the big states like Texas and North Dakota and such, and it's primarily because those states have cheap and abundant deep injection wells. So it's more expensive to do what's happening in Pennsylvania than it is to do deep injection. But anyway, a good news example, greater disclosure of the chemicals in fracturing fluids through frac focus and otherwise. So it's not true. You hear some people say there's no transparency. That's not true. There are trade secret exemptions that are typically claimed on a well, half a dozen, so there's not full transparency. But I think full transparency, or the more transparency we can get, is a good thing because it will lead to phase out of the most toxic chemicals. It will also help companies get credit, the companies who first phase out the most toxic chemicals too. You know, increase public trust, if you will. And then finally, good things going on in green completions and the elimination of open wastewater pits, at least in cases where that's economically feasible. So that's new wording in the new rules that have just come out. All right, let's talk about water quantity then. So first of all, you don't have to be a genius to know that the number one filter to look through this is just whether you're in a dry area or a wet area. I showed you that picture of the Marcellus at the beginning. Here's another one I took from a helicopter on the right. That's an open wastewater pit you see here in the right. And then there's a picture from the Eagleford on the left, not mine in this case. So about twice as much precipitation in Pennsylvania. My former home state of North Carolina, we just finished doing a baseline water sampling campaign there that's just coming out now. Another relatively water-rich state. But in these drier states, it's more of an issue, and in the drier states, it tends to be more groundwater pumping, which is a little different issue than surface water pumping. All right, so I also mentioned up here that it's water intensive, 1 to 7 million gallons of water to hydraulically fracture a well, about 7.5 liters of water for each gigajoule of energy that comes out of the ground. We'll talk about that. But the perspective is strongly dependent on scale. And what do I mean by that? Well, if you look at a national level, or if you look at a state level, then the amount of water that goes to hydraulic fracturing is pretty small, typically 1%, or even slightly less than 1%. And most of our water, of course, is going to agriculture as the number one use, and also to cool our thermoelectric power plants in many cases. And then municipal is a distant third. So compared to those sources, the water for hydraulic fracturing is quite small. But when you start talking about individual counties or individual streams and withdrawal rates and things like that, then it's a different story. And for individual counties in states like Texas and elsewhere, it can be anywhere between right now about 10 or 40% of the total groundwater pumping from that state, and of course a new demand on that water in an area that's in many cases is relatively water poor. So more locally, it's a much bigger issue, and it's especially an issue in dry places where that water is coming from groundwater pumping. And if you look at the build out of some of these counties, in rare cases, there are counties that look like they're going to have to import water. This is based on work by Bridget Scanlon at the University of Texas, for instance. It looks like they may have to even import water to fulfill their needs. There isn't enough groundwater that they could pump in some cases, but that's rare. All right, so a lot of water intensive, obviously matters whether you're in a dry or a wet state. Now let's compare it to some other things. This is a paper that just came out last fall. We did this as an annual review. So the surprise here for some people is that, yes, it's water intensive, but you also get a lot of energy back out of these wells. And it's not enough just to know what the water use is. You have to have the energy use to have the denominator for that comparison. So water use per energy generated. So for instance, one unconventional hydraulically fractured well uses more water, but if it produces, if it uses 5 times more water and produces 10 times the energy, then that's better than 10 of another source, if you will. All right, so hydraulic fracturing, unconventional energy, horizontal drilling it's more water intensive than renewables, like solar voltaic and wind. They use essentially no water, but less water intensive than things we're more comfortable with. On the East Coast, we have a lot of pulverized coal, and the pulverized coal water use is about 2 or 3 times as much for extraction and processing, and about 2 to 3 times as much at the actual power plant stage. So water use per gigawatt of electricity. Same story for nuclear. All right, nuclear is more water intensive, and both for the extraction stage and the processing and at the power plant. Placed in that context, all of a sudden those 1 to 7 million gallons look a little bit different. And that's not to downplay those water demands, and I have already said that there are other fuel choices that we have, like renewables, that are low carbon, low air pollution, and low water too. But it's this context that I think helps me at least understand some of these different fuels. And there are some exceptions in the renewables area. And you look at biofuels in particular, and that high water demand is coming primarily from the transpiration of the plants, which is a little harder for me at least to know exactly what to do with. But per unit energy at least, biofuels is the most water intensive. Okay, so a little different way of looking at it. Let's look at some water quality interactions. So we spent a minute on quantity. Let's do quality. Here's a typical well pad or operation, if you will. Where might some water interactions come? Well, you've got a stream or a pond or a river here. It might be used to provide that water for the hydraulic fracturing operation. You have an industrial operation going on here, like the one I showed you in the photo, the possibility for chemical spills. For instance, those chemical spills might reach that water, they might not. You have, in this case, a water storage area. Could be an open wastewater pit, like I showed you in that earlier photo. And then you've got the shallow groundwater source here that we've been focusing on. And of course, the hydraulic fracturing is going on in most cases deep down underground off this picture, a mile or two underground typically. So the point of this slide, and the point of our work and lots of other folks' work, is that the focus, I believe, really should be on these surface operations and the upper 500 feet or a couple hundred meters, if you will. So we really ought to be paying more attention up here. Well integrity, for instance, will come to, and some of these surface operations from a health and environmental risk standpoint than the deep hydraulic fracturing. I'll tell you as we go along why I think that's the case. So one of the things we've done in my group, so let me mention Avner Vengosh, my colleague at Duke, many other people, you see some of them listed here. We did the first studies to look at drinking water quality and hydraulic fracturing. So we asked a simple question: is your drinking water any different if you live near to a natural gas well than if you live farther away? We started in the Marcellus and then have moved into some other plays around the country. This was work in Arkansas, led by Tim Cressy of the USGS on this paper, and then Nat Warner, who's a grad student, for a follow-up paper. So in Arkansas, we sampled, it wasn't a huge sample, about 100 houses in this area. We looked at relationships with distance to natural gas wells. We saw no difference in people's drinking water. These are people on private water wells, not on municipal water wells, because for municipal water, that water gets tested regularly. But if you're on a private water well, like I was in North Carolina, nobody tests your water unless you pay to do it, and there really aren't any rules or restrictions on that water or on that water quality. They're just guidelines. So all the people that we tested were on private water wells, and in Arkansas, we found no evidence for any change in water quality whatsoever. So it didn't matter if somebody was living near a natural gas well or a long way from a gas or oil well. And that was true for salts, for metals, for radioactivity, and for stray gases as well. We did not look at hydraulic fracturing chemicals, organics, in this particular set of studies. All right, so that's a good news story. In the Marcellus, the story was a little bit more nuanced. And these were the first papers that we did, and have continuing to work there over the last 5 years. So here now, for those of you who know this area, some of you are looking at a map of the northeastern corner of Pennsylvania. The green is New York, the blue is Pennsylvania. That state boundary is interesting and useful to us because it's like a fence line comparison, where you have the northeastern part of Pennsylvania, where there's been an intense amount of drilling. This is mostly a dry gas area for natural gas, but across that state border, New York's had a moratorium on high-volume hydraulic fracturing. So we can use that to understand in a very similar geology right across that border, similar conditions, but with a different set of operations going on. And of course, New York as a state just passed a permanent moratorium on high-volume hydraulic fracturing, at least until some other administration comes into power. All right, so what you're looking at here is just a subset of the places we've sampled. Each blue triangle is a house. The red are wastewater samples. The New York samples are in boxes. So we sampled these different sets of homes and looked at their water, and then tried to address that question of any potential changes in water quality. All right, before we come to that, let's try and understand some of the shortcomings to this work. Shortcoming number one, we didn't get there before the drilling started. Right, so in every case, what you would obviously want to have is a pre-drilling sample, and then see if that water quality changes through time. Right, so we didn't have that. The drilling happened several years before we or anybody else had done this work. So at one level, you can say, well, that means you can't say anything. I don't think that's true. I think you can say something statistically, and let me show you why I think you can say that. You're looking here at a figure of salt concentrations, that's chloride on the x-axis, And methane concentrations normalized to argon. Argon's a noble gas. I'll talk about them in a little bit, but an atmospherically sourced gas. What you see here is two populations that fall upon this relationship from sort of high quality water in the lower left to poor quality water in the lower right. So you see everything in this set of samples from that northeastern part of Pennsylvania. You see people have super good water quality down here, and when they have super good water quality, they don't tend to have any methane in their water to speak of. Then you've got some folks naturally who have pretty lousy quality water. They're over here. And when they get very high salt concentrations, this is just chloride as an example, they also tend to have naturally occurring high methane concentrations. These are the folks who say, my grandfather used to be able to light his water on fire, naturally. And those cases are true. All right, and then the other interesting thing about this relationship that we generated is that it doesn't make any difference whether you're near or far to those natural gas wells, and that's different in this kind of oil and gas extraction, of course, because these well pads aren't being placed because someone is sniffing for natural gas in that location. This is like a chessboard, and the companies are covering the landscape in that checkerboard fashion, just as they do here. So you wouldn't expect any difference between this background water quality, whether they were living near or far, and that's what we see statistically. Okay? Then there are the oddballs. And the oddballs are the ones I've circled in green. So these are oddballs in hydrocarbon space, in the methane concentration, in the ethane concentration, and to some extent they're hydrocarbon isotopes, but especially in noble gas concentrations. And in the last couple of years, this work, especially with Tom Dara and Bob Prada of Rochester, so the noble gases have been useful for us because the noble gases aren't transformed, they don't react, and they're only sort of a small, narrow set of fractionations that occur for the noble gases. So they go along for the ride, if you will, and give you an extra toolkit, an extra set of things that you can measure to be able to distinguish deep gas from intermediate gas from gases that are at the surface that are influenced by rainwater. All right, so the noble gases, all these ones show anomalous hydrocarbons and anomalous noble gases with different deep sources. All those green points are within 1 kilometer of a natural gas well. And for this and many other reasons, including plots that we've generated of methane and ethane with distance to a natural gas well, we believe that that's sort of the distance for which, at least in this system, potential contamination occurs. And I want to be really careful about it. It's a minority of cases of people within 1 kilometer. So most people within a kilometer are not having trouble or changes to their water quality. But there is a minority, a subset, whose water quality does appear to change. All right, where's the gas coming from in those anomalous cases? Well, here's another example of how we could use, in this case, noble gases, helium-4, in this case, a ratio of helium to methane, distance to natural gas wells on the x-axis in kilometers. So you see the background spread for people across this area up here in the ratio of helium to methane. Here's a naturally occurring salt spring, a place that the gas bubbles up to the surface, briny, generally poor quality water, just like we were looking at before. And then you've got these people down here, again, all within a kilometer or so, whose water has very different helium signature in it. Here are the source gases, intermediate gases, not Marcellus gas, but younger, or at least shallower upper Devonian gases. Here's the Marcellus gas. And you can see here some homes have ratios and hydrocarbons and noble gases that match up with that Marcellus signature. Others have ratios that match up with this upper Devonian signature, again, all within these shallow distances. Okay, I'll talk about this. We believe that this is attributable not to hydraulic fracturing opening cracks that allows gases and potentially, and even much less likely, liquids to move from deep underground up to the surface. This is an issue of casing and cementing. All right, so when you got bad cementing, the annulus that protects the outside of that well between the rock wall, you have a pressurized pocket of gas that might move up and out into shallow groundwater. That's what we believe is happening in these upper Devonian cases. And to get the Marcellus gas that matches, again, in a rare minority of cases, we think that's indicative of a casing leak. For instance, the threads on the metal pipes that might leak. All right, here's a schematic of some of those mechanisms. You've got a couple of naturally occurring processes up here on the right for how methane can get into groundwater. You have you have here, let's say, this is the cement, the annulus approach I just mentioned. So if you had a gas-rich pocket, some of these gases would have been the pockets that were extracted 25, 50 years ago in some of these areas. the shallower ones. Okay, if that pressurized gas, if the cement is bad, has cracks or such, can move into, up, and out without ever having any contact with the inside of the well or the gas that's coming from here. So in that case, you'd never expect to see hydraulic fracturing chemicals or anything else because there's no fundamental breach in the casing. And then you got a subset of these guys here who we think are casing leaks where the gas is moving into and up and then out through a breach in the casing up there. And in very rare instances, and not so much in this part of the country, but there have been a few documented cases in this part of the country where an abandoned well, an old oil and gas well, has contacted the drilling operation in some way. But our data don't suggest that this is happening. And we can tell that apart, conceivably, because of these changes in noble gas ratios and other things. So those gases would be moving through layers of water and such. Okay? So let's go on. So I like to think of this in some sense as the exceptions. I view our job in the environmental science community to understand the exceptions. Why, so we had about, in that last paper that Tom was first author on, about 8 clusters, different locations of places that the data suggests contamination with hydrocarbons. 4 of them look like shallower gas and cement issues. 4 of them look like casing issues. If I had to pick one or the other, I believe that cementing is a bigger issue than the casing leaks. Okay, so those were the examples. Why might those happen, and what are the exceptions? Well, here's one very publicized, highly publicized exception. Many of you have heard about this. This is the case in Parker County, Texas. So what can we learn from exceptions like Parker County? There it's just southwest of Fort Worth, about an hour. This is a case where a homeowner claims to be able to light his water on fire and where a neighborhood has had what they believe to be some problems. So we sampled there as part of this test with noble gases. In that neighborhood, we actually saw a few houses change in water quality to go from good, high purity water all of a sudden to have 10 or 20 times the amount of methane in their water and to bubble. What's going on there? Well, one thing is that the company who drilled those 2 production wells put no cement between about 400 feet and about 4,500 feet. So that means the annulus is empty. If you think about those pressurized pockets of gas, that gas is free to move up or down that well bore, up 400 feet. Even if the top 400 feet has perfect integrity, you're very close to the surface now in a relatively fractured limestone area. So that gas can move out and up into people's water. That's what I believe has happened here. The Texas Railroad Commission, they issued a report almost a year ago. Their quote was, based on the evidence of increasing methane concentrations in some water wells in the Silverado neighborhood, Railroad Commission staff recommends that residents properly ventilate and aerate their water systems. Now that's a curious conclusion for environmental scientists. I would think for an investigation that they're not evaluating or an investigation that's closed, the first half of that sentence would lead you to go, methane concentrations are going up, let's figure out what's going on. And I think the figuring out what's going on is important in cases like this, and in Pavilion, Wyoming, even more controversial, some of the other ones. I think this is really important because if the people in these places don't believe that the regulatory agencies are taking care of them and really looking out for them, then they have the potential to lose confidence in those agencies. And then you start to see a backlash, if you will, against some of those agencies. So in my view, we ought to be going after these as hard and as deeply as possible and as quickly as possible, figure out if there's anything going on, and if there's something going on, figure out why and learn from it. All right, another issue we've looked at a bit is well integrity. This is a paper led by Richard Davies. This is an analysis that takes basically 100 years of oil and gas wells, really apples and oranges, very hard to combine quantitatively, onshore, offshore, older, newer, different materials and such. But in this analysis that Richard led, we find a few percent, after a few decades, that a few percent of wells, up to a few tens of percent of wells, have at least sustained pressure. That doesn't mean that they're leaking into the environment. So thinking about these legacy issues is something that I believe, as an environmental scientist, we have sort of the responsibility and the luxury to think about, because I don't have to deal with quarterly reports and profit statements and things like that. So I'll give you an example here. I was out in Pennsylvania last week. Mary Kang's a postdoc in our lab. She published, while she was at Princeton, the first paper looking at methane emissions from abandoned oil and gas wells. These are 4 wells, all on one property, about one 50-acre property in Pennsylvania. Nothing to do with hydraulic fracturing here, just before I forget to say that. These are old wells. So you see this kind of thing. So that's almost pure hydrocarbons coming out of the well.
That one they claim grandfather in.
Go back, sorry. The one in the lower right is a different example. This is one that was plugged in March of last year and plugged badly. So the state's going back in to do that again. So you just see the proximity of some of these to the houses and such. So thinking of, what are we doing, if anything, today that we might wish we weren't doing or wish we hadn't been doing in 25 or 50 years? And that ought to be on the list too. Finally, on the water side, let's think about wastewater, and I won't spend as much time on this, but in some sense, the wastewater issue may be, from a potential health standpoint and a potential environmental standpoint, may be the biggest issue for this high volume that I mentioned, this almost trillion gallons. I mean, the wastewater is much nastier than the hydraulic fracturing chemicals and fluids that generally go into these operations. All right, it tends to be old, it's very salty, Marcellus in particular, about 10 times seawater. Often has high bromide concentrations. As most of you know, you get bromide in the environment if it associates with chlorination and drinking water treatment. It can cause carcinogens. In some cases, high concentrations of toxic elements like barium and arsenic and selenium. Radioactivity norms, naturally occurring radioactive materials that are there in relatively low concentrations, but can be an issue if they build up in scales, in pipes, or in the solids of, say, waste treatment operations. And then, of course, organics as well. So what do different states do with this wastewater? Most of them deep inject, as I mentioned. Half a dozen states in the US still make it legal to spray that wastewater on land or to use it for dust control. I'm an environmental scientist, so I have the luxury of saying I think that's a bad idea. Hall 2 municipal wastewater treatment plant, no longer done much at all. Used to be done more, but those public treatment facilities are just not set up to handle the volumes or the chemical mixtures, if you will, that are in this water. Two options that are used increasingly, especially in that Pennsylvania example, are hauling that water to a commercial wastewater treatment facility where most of the solids and such are taken out, and then you have to dispose of those solids. And then, of course, the best one of all, reusing for a future fracturing job with or without treatment. And that one can only go on so long as you are continuing to hydraulically fracture new wells. So there comes a point in time when that won't apply. But for now, that's a good thing. Some examples on the wastewater side. I picked this just because it's a Colorado example, and I don't know the investigators. They could be here for all I know, actually. So Gross et al. They published this paper a year or two ago looking at open wastewater pits in Weld County and documented 77 spills, about 1/200th of active wells that affected groundwater over a 1-year period for Weld County. The good news here, I believe this is correct, I didn't check the paper before I came, but I think in about 80% of the cases the groundwater quality was fine 1 year later. But I still had about a fifth of the cases where that wasn't the case, I believe, and don't quote me on that. And then some work that we've done, this is led by Nat Warner and such. This is, again, a relatively confined case. So what we did here was to sample upstream at and then progressively downstream from one of these private wastewater treatment facilities in the Marcellus in Pennsylvania. And what you're seeing here is a graph that has radium-226 and radium-228. So these are radioactive elements. You're seeing near the effluent discharge here. So the upstream and background levels from other rivers are down here. So you see low concentrations. These are log-log scales. Downstream of the discharge, but right near the effluent discharge, the values were much higher. And the sediments in this case, for a few tens to hundreds of meters, were about 200 times the background concentrations. And this wasn't an effect of the facility doing anything wrong. It was an outcome of just having a lot of water go through it, and then having this radium in that water that sort of gloms onto those sediments. So the company announced that they're going to dredge the top couple hundred meters of this river and take that away. Once you got about 2 kilometers downstream, the concentrations of most things were back to normal, with the exception of bromine and to some small extent chlorine. Anyway, that's just a specific example, but associated with a treatment facility. All right, so 3 overarching recommendations here. Gather as much pre- and post-drilling data as possible. It's not just true for water, but air, natural gas itself, its composition and such, and ideally health too. Make most of that data available. Keep track of everything, what's in the materials, where it comes from, where it goes. The locations of old and abandoned wells, again, making that information as publicly available. And then protecting landowners and consumers through a combination of best practices that you're seeing, rules and regulations, and education. And I'll show you some examples, especially in the last portion of this talk, where what different companies do, best practices, really makes a big effect on the environmental outcomes for these things. So let's take the final third, if you will, and talk about air a little bit. Our group is doing work both upstream and downstream, and then lots of other folks here are doing work. Joe Von Fischer's in the back. He's done work associated with downstream leaks and other kinds of leaks. Lots of work in Colorado, obviously. NOAA, you've got UC Boulder, and CSU too. We'll go through a couple of these examples. So what are people concerned about for air? Well, there's on-site workers, clearly, that they might breathe, and that's no different from a well pad or the floor of a manufacturing facility at Dow. There are compressor stations, processing, booster plants, the drilling and well completions, holding ponds, and such. And one of the issues, one of the concerns is what might be into the air, whether it be, in this case, silica dust, primarily for workers. That's the haze that you see there. But I think one of the concerns, and one thing we really don't know much about, is the potential for volatilization of chemicals from, for instance, these open wastewater pits that might move up into the air and then blow downwind from this facility. And to not have much information is not the same thing as saying that this is a major problem. I'm just saying we know very little about this, about that potential pathway. But I think that's one of the things, one of the areas that in my view is the biggest uncertainties from a health standpoint, is that we need more monitoring of air quality near these operations. All right, there are some good things going on associated with natural gas extraction in particular compared to coal for power use. So 90% less sulfur dioxide and mercury, less particulates, about the same amount, and then a lesser reduction of NOx. And these are things that kill people. And conservatively 10,000 people die each year in this country from the pollution associated with coal-fired power plants. This is one of the reasons there's such a big push in China for extracting more natural gas. China's so desperate for natural gas, they're actually using coal to make into natural gas in some of their provinces. All right, so again, it depends what you compare it to. And one of the things we have to think about is what this additional natural gas and oil will replace. Will it replace coal? Which is probably a good thing in almost all circumstances environmentally. Will it replace wind and solar? Something that's not good from a greenhouse gas or water or air pollution standpoint. So it's that balance, or something in between. All right, here's not work of ours. This is Dave Allen's work at Texas. They looked at well pads around the country. So imagine scrambling over these well pads and using chambers and big plastic bags and things to look at the actual emissions that are coming from things like valves and pneumatic controllers and pipes and things like that. Well, that's what they did here. What they found on these about 200 sites was that emissions were about in line with what the Environmental Protection thought they should be, and maybe even slightly less. So that was good news, because there's been a lot of controversy about the extent to which methane and natural gas emissions might be considerably higher than what the EPA thinks. Well, from these bottom-up studies, that's not the case. Most interestingly for me, threefold variation in well completion emissions. Now, well completion, that step where the gas and oil are made available and then go to the pipeline. So the practices of different companies made a big difference in the amount of emissions to the atmosphere in these cases. It stopped. All right, another Colorado example. In fact, I'll have a couple nearer to home here. This is work out of the NOAA group, led by Gabby Petrone. What they did was, and I'm sure most of you have seen this work, they used this observatory, the Boulder Tower here. They were just doing monitoring work of air quality. And what they noticed was that when the wind blew from the south, they had higher concentrations of methane and things like ethane and benzene and such. That was expected because that's pollution from the Denver Metroplex. What wasn't expected in their study was what happened when the air blew from the northeast to the southwest, where they also saw higher concentrations. In this case, they also did some groundwork with cars, but they found that VOCs, benzene, and methane were 2, 3, and 7 times higher than the state inventory suggested they should be. Right? Now, that's not going to be true everywhere, and it isn't true everywhere. But there's something going on in these operations, and of course, Colorado's done a lot in the last couple years strengthening its air emissions rules and regulations. Right? So this is a top-down study, if you will. This suggests emissions might be higher than the state or the EPA suggests. And then one I put up just because it's at least exposure relevant, another Colorado example, Lisa McKenzie. And what they did here was to measure air quality, to do air monitoring near oil and gas pads, and what they found was just higher concentrations of these compounds in the air for people living within half a mile. No health components to this study or anything else, but just thinking about potential exposure. And I said there's almost literally no work that's been done in this area, at least in the peer-reviewed literature. So we really don't know much about this at all. We have to think about identifying large emitters quickly. So early detection is a key here. We can use, for instance, infrared cameras. This is work that EDF is leading. So imagine flying operations using infrared cameras to detect emissions that are invisible to the naked eye. This is just an example of a well pad. You see those emissions coming off a tank. Now that's unusual. Again, this is all about that long tail. It might be 0.5% of operations up to a few percent, whatever that number is. So it's really about just a handful of cases, a low proportion or percentage of cases, that if we can identify those cases quickly and cheaply, you can really make a big difference to reduce those leaks. All right, so sensor development is another area that's really important right now and where there's a lot going on. Last example, let's talk about downstream. No longer talking about hydraulic fracturing either, because once a methane molecule or an ethane molecule is in the pipeline, it doesn't matter where it comes from. But we've also done work with distribution lines downstream. Joe's actively worked on this as well here. Let's see, so you imagine a car. So that's, in this case, a Picaro analyzer on the right. So imagine putting a high-resolution methane instrument in the back of a car with GPS, anemometer that gives you wind speed and direction, and then literally driving that vehicle every block around a neighborhood or a city. So that's what we've done. If I think of it, I'll remember why the cop's up here in a second, I'll tell you. If you see a big ping concentration, you might hop out of the car and try and figure out where that gas is coming from. Is it a manhole, a curb, out of the soil? This is work led by Nathan Phillips, Boston University. This was the first publicly available map for such a operation. So red is the road miles driven. So we put this instrument in the car, drove all 800 road miles block by block in Boston. The yellow are the leaks detected by the car. So there are about 3,400 of them. Number one predictor of leaks, really not very surprising, old cast iron piping, old infrastructure. So we've got a lot of old pipes in this country, old water mains, old bridges and roads. And that's the story for this Boston study. Will that apply everywhere? No, because not every city in the country has old infrastructure like this, and other cities have done more to repair, for instance, their infrastructure. But that gives you an example of what we find. And again, the spirit is to make this data, this information available to people. The day after this paper came out, the mayor commented on it. At that time, Congressman Markey, now Senator Markey, commented on it. He's been interested in that issue for quite some time. July of last year, Massachusetts passed a new pipeline safety bill that accelerates natural gas replacements. So helping companies front load some of those repairs and replacements. We just published in January, this is work led by Catherine McCain, a grad student at Harvard, and Steve Wolfsey's group, a top-down budget for Boston. So it's really hard to go from 3,300 leaks to know what the total emission is to the atmosphere. There's a lot of error associated with that. So another way that you could do that was to imagine putting some sensors on top of some buildings in the city, and then also measuring air quality outside the city, so that when the air blows into the city, you've got a relatively clean picture out here, and then you can look at the concentrations building up in the air over the city in a couple of these buildings. That's what you're seeing here. And if the natural gas, if the methane that's in the air over the Boston Metroplex is coming primarily from natural gas, then you ought to see not just the methane, but the ethane that's associated with it, and you ought to see it in the same ratio as what's in the pipelines. Right? And we know what's in the pipelines because it's publicly available. That's the blue line. Each of the dots is a day, an average day, and the red line is the slope of that relationship in winter. So in winter, about 90% of the methane in the air over Boston looks like it's coming from natural gas sources. In the summer, it's about 60%. The total emission's about the same. It's just in summer, you've got more methane generated by microbes in sewers and capped landfills and other situations, so biologically generated methane. All right, so that gives you sort of some estimate of the budget. In this case, the estimate is about 2.5 times higher than the state inventory suggests it is. Now, what we don't know is that that's all coming from pipelines. We have pretty strong evidence, I think, that it's natural gas, but we have no data, literally, for losses after the meter. So it's also possible some of this is leaking out of buildings, could be leaking out of imperfect stoves, like the range in my house, so we really don't know where all that's coming from. Okay, last example, Washington, D.C. So we published this last year. So here in Washington, we found about the same leak densities, higher concentrations, 6,000 leaks across the city. That's Capitol Hill that you're looking at on the left. The right is an app that the Washington Post did based on our data, so people could plug in their address and then see what leaks are around them. So same story here, old pipelines. All right, how can you use this information? Well, you can use it to start with to prioritize fixing the leaks. Top 50 leaks are shown here, at least in terms of concentration. It's not feasible for, to make a recommendation, go fix 6,000 leaks, and the distribution companies around the US have invested a lot over the last 2 decades in making their infrastructure better. But we can use this kind of data to say, well, where might we find the largest, highest emissions, or perhaps also the most dangerous sources, then fix those. That's one possible use. Another justification is safety. So when we were doing this initial survey, the top 20 concentrations that we found in the car, we hopped out of the car and sampled the gas to find the source. So in this case, 12 of the 20 manholes, we found these in manholes. 12 of the 20 cases, the gas was present in explosive concentrations in the manhole, not in the air. But unusually, when we called those in, we went back 4 months later, and 9 of those 12 hadn't been fixed, right, which was something of a surprise. There's one with 23% methane in it. That's 230,000 ppm methane. Companies, there's a big difference in the amount of lost and unaccounted gas that they report. So each company is required to report how much natural gas is lost from what enters the city and what's metered. That does not mean that all this gas leaks to the atmosphere, but you just see a big range. The average for the US in companies over 1,000 miles of pipelines is about 1.6%. Boston and DC are in the 2.5 to 3.5% range. So I think this kind of information averaged over a decade like this tells us something about which cities might be the leakiest. Finishing up, it's always important to ask who's doing a good job. So here's a graph I did last fall. This is the y-axis is the number of years to replace the cast iron pipes in the system of a given city, and the cities are listed on the x-axis here. So what are we talking about here? Well, imagine taking all the reported data for pipeline replacements and looking at the rate at which those pipeline replacements are being made and comparing that to the number of miles left to be repaired. So you see some great examples here. Cincinnati, Ohio is one, where the state of Ohio had, for the last 15 years or so, a program of accelerated pipeline replacement that was a partnership between the company, in this case, I think it was Duke Energy of Ohio, the Public Utility Commission associated with it, and the state and municipality to phase out that cast iron pipe. And they sort of slogged away at it year after year. But now they're almost done. They're only 3 years away. The other side of the spectrum is Baltimore, Maryland. At the rate that Baltimore replaced their old cast iron piping for the last decade, they'll be done in 2150, when all the rest of their pipeline will be 150 years old. Right, so there's a wide range, again, in what different companies have done here. All right, and then finally, and I mentioned Joe a couple times, he's been working a lot in this area too. We've mapped some cities where they've replaced the pipeline networks, and they really make a difference. In this case, these repair programs lead to a 90% reduction in leak densities. So these programs work. Right, so justifications for fixing leaks like this: money. Consumers pay $2 billion a year for that lost gas because the consumers, the ratepayers, pay for the gas that leaks out of the system. But the companies are capped in what they can pay, what they can spend on repairs by the public utility commissions. So there's a sweet spot there in helping them sort of front load repair, but long-term weaning them of being paid for gas that leaks out of their systems. So money, jobs, 4 unions are associated with repairs and replacements, safety, rare cases, fatalities, and $100+ million in property damage. And I'll say it again if I haven't already, the record of safety over the last 20 years in the US is much better. They're about half the fatalities that there used to be 20 years ago. Air quality and health, hydrocarbons can catalyze ozone formation and even climate change and greenhouse gas emissions, but you don't have to have that or even believe in that one to have those other 4 reasons to do something about this. Okay, I'll stop there. I always like to think about where our energy will come from. This is a picture of a mountaintop mine I used to fly over when I flew, say, from North Carolina to the Marcellus in Pennsylvania. That's a pretty invasive way of generating your energy, in this case from coal. So we have choices about our energy, and we'll make those choices based on societal decisions and obviously money, and I hope as much we can the environment. Thank you for your time.
Questions to start with.
We're doing cards.
Yeah, we're doing cards. If you have questions, pass them to the center. We're going to have people picking them up, and we'll try to get as many as we can answered.
These are from multiple people, or is each card one person?
I think they're multiple.
Okay, first one. How transparent has the industry been with you in your research? Well, that's an easy one to start with. First of all, I'm a middle child, right? So that means when I sit down at the Thanksgiving table, I've got a FBI older brother and a ultra-liberal, well, I used to say legalize hemp, now you're in Colorado. It's like, that's not an issue anymore. But I have an ultra-liberal Roswell conspiracy theorist younger brother, and I'm a middle child trying to sort of keep everybody happy at the table. And working for Dow, so I believe fundamentally that companies are by intent are trying to do the right thing. And especially when our first papers came out on water quality, the pushback was pretty strong from some of the companies. I will be honest. I think the 4 years of our work has shown that I don't believe it's an existential threat to hydraulic fracturing. I don't believe, and I'll say it quite clearly, I don't believe that there's something fundamentally flawed about hydraulic fracturing, that it can't be done safely. I believe it can be. I just think that it isn't always done safely, and trying to understand those exceptions is important. So it's been rough at times, but once in a while I get beat up by the environmental community every time I say anything nice about hydraulic fracturing too. So, okay, you have an important question number 2. You have an important list of recommendations, but 10,000 wells are already in Colorado. Is it too little, too late? No, it's not too little or too late in my opinion. Many of those wells, of course, are older. They're put in place with different sets of rules and regulations, but my perspective and the perspective of many people here and elsewhere in the state is to try and make things better. So that's the spirit of some of the rules and regs that have been put in place. So my answer is no, it's not too late. Can bromides in wastewater migrate to the atmosphere, and will this contribute to ozone depletion? Not likely. Okay, I'm not even screening these. It seems that the most danger to the environment is what we can't predict. What are you concerned about most in long-term impacts? Well, that's a good question. Well, I'm a climate scientist too, so I come from a community of people, so 97, 99%, whatever percent you want of people in our community believe that climate change is real, and I think the evidence is very strong for that. So I have concerns about our long-term greenhouse gas budgets and emissions and the benefits from renewables like wind and solar. So I'm concerned about climate change. Natural gas could help us in that transition, could hurt us depending on what it replaces. I'm perhaps most concerned about maybe with those legacy issues. So 2 things: wastewater, what we do with it, and we have a lot of experience in that. But the legacy issues of the notion of having an extra hundreds of thousands of additional wells and keeping things safeguarded, and states not investing sufficiently, in my opinion, to safeguard those wells in the future. Well, what's an example? Well, Pennsylvania takes in about $250 million each year, at least they have in previous years, based on their production in impact fees. So that's about a third of what comparable states would take in based on the amounts, so it's not very much. Almost all of that, not surprisingly, goes into the general coffers for the state. About 10 million of it is spent on the environment. Most of that is spent on things today like parks and other things, and that's fine. But there's no bank account. There's no set of CDs that we're investing and setting aside to deal with legacy issues in 25 or 50 years. And as an environmental scientist, that's what I think we should be doing. In the same way Pennsylvania deals with acid mine drainage today, or those kinds of old legacy wells that I showed you. So really thinking long-term and trying to minimize those long-term impacts is something that I think is really important. Can your groundwater results from the Marcellus and other basins be extrapolated to the DJ? Is the geologic setting of each basin unique enough so that this extrapolation would be dangerous? Well, first of all, you can't, we wouldn't, and you can't extrapolate to a different basin where you don't have any data. I mean, there are some generalizations. If the geology is more fractured, so northeastern Pennsylvania has a really fractured geology. That place in Fayetteville in Arkansas that I showed you our early results from, where we didn't see evidence of contamination, geology is less fractured, has better seals, caps above and below their aquifers, the conditions are better. So if something goes wrong, or if a person makes a mistake, or if somebody gets in a hurry, the consequences are likely less in that situation than they are in a place where the connectivity is bigger, like in northeastern Pennsylvania and some other places. So we can say something about it if we have basic geologic information, if you know something about faults and such. But you couldn't, or I wouldn't at least, extrapolate to what would happen here. And there's some work being done here on water sampling, I know. How is methane held in shale, and how do fracking chemicals cause the methane to come out? Well, I'm not a production geologist, but in simple terms, as most of you know, the water, the chemicals, the proppants are pumped underground at high pressures, high volumes. They crack open that shale. The sand and the proppants are left in place to keep those cracks open, and they basically increase the permeability of that rock and allow the oil and gas to flow to the surface. As I said, I'm not a production geologist. If concrete and steel bridges are collapsing, how long do we have before the, something and steel well casings, I don't know, and steel well casings, tens of thousands of them deteriorate to the point that our potable groundwater supply is adversely affected? Well, that's essentially that's one of these legacy issues. Long-term consequences of cement in particular are hard to predict. It's not true, it's not the case that all cement breaks down over time. It does change, but you have plenty of cases where wells seal back up, where they actually the seal actually gets better, closes up through time. Our review of well integrity and such suggests that there are these, that this is a serious issue when you get to decadal timescales. So there's a subset of wells where the cement, for instance, is bad from the start or has problems from the start. That's a different situation than deteriorating cement through time. Without the financial, you tell me when you've had enough. Somebody tell me when you've had enough. It's like, when is he going to stop? Without the financial consideration, what do you propose as a solution to this continued rampant exploitation and destruction of ecosystem and its services? A national energy policy. That might be a loaded question. Yeah. I don't really know how to answer that. Like I said, for me, it's never about. It's not one thing that's ever good and bad. I have to have a context for that question. Is it better or worse for water availability and potential water pollution and air pollution and greenhouse gases and things like that? And I've already said that there are options out there that are better. Low carbon, low pollution, low water, and there are options out there that are worse, in my opinion, that we're using a lot of in this country. And globally, coal extraction and use is still expanding around the world, even though that's not true here in the U.S. Am I paid or contracted by any oil or drilling companies to do this research? Where does your funding come from? Well, that's a fair question, and it's just as fair on the other side of the ledger, too. Our funding is mostly, so we've been funded by the National Science Foundation. We've not received any work from companies. That doesn't mean that I wouldn't or haven't worked at all with companies. I think ultimately, for especially some of these detection cases and solutions, you got to work with the people who are actually drilling wells for a living. Somebody has to. So I think that's important. Already done these. It's like, is it Letterman or who's it Leno? It's like.
No, I have to go chase them.
No, I don't think I'm Leno. Trust me. Nor do my children. What is the biggest issue that you believe can be addressed and solved by industry today? Well, gosh, that's a good question. Yeah, well, let me go back to sensor technology. I think investing in tools to do more monitoring, spending a little more money on, say, leak detection, groundwater quality issues, maybe even health effects, making that investment up front. If you genuinely believe that these processes don't cause problems, then the more data we have, the more evidence there ought to be for that to be the case. So I'd like to see I'd like to see more monitoring and especially sensor technologies to try and find those outliers, the exceptions I call them, and identify them more quickly. Could you compare leak emissions from pipes to permafrost melting? Not really. I don't know if the context for that question is in the future, for instance, potential warming. All right, let's try this. Globally, natural sources of methane are big from wetlands and such. In the US, the largest anthropogenic source of natural gas is oil and gas, of methane to the atmosphere is oil and gas operations. In other places around the world, and I think globally, the biggest source of human-caused methane emissions is ruminants like cattle and such. So there's a lot more methane, a lot more potential for liberation to the atmosphere from the permafrost, but we're not yet, to my knowledge, at the point where that sort of permafrost melting and really sort of catastrophic is not the right word, could be the right word, but there's no evidence for that yet. But that sort of rampant loss to the atmosphere is not happening yet, to my knowledge. And if anybody has a better answer than that in the audience, now's your time to chime in. Seriously.
About the blowholes in
Well,
Siberia?
I've heard about blowholes and all that, but what I have not seen is a suggestion based on the inversions, the global models and such, and the monitoring of air around the world that suggests that that's yet of global consequence. So it's a huge concern. But there's, again, to use a Colorado example, people like Peter Tons here down in Boulder are leading global monitoring networks for methane. All right, one or two more, and let's call this quits. Can wastewater be processed to clean drinking water? Yes. Just depends what you want to pay for it. It almost never happens, even in California. And our water's in deep trouble because we've just gone through another winter with very little rain. Can you comment on the methane impact on climate change relative to renewables? In terms of climate change, aren't we greatly slowing the necessary transition to renewable energy? All right, first part, can you comment on the methane impact on climate change relative to renewables? Okay, so relative to at least solar PV and wind, the greenhouse gas emissions and the methane emissions associated with natural gas are a lot higher. All right, say it again, compared to, say, coal, the CO2 emissions at the combustion point are a lot lower for natural gas, so perhaps 50% lower, maybe 60% lower. So that's a real potential benefit, and if you can clean up and reduce the leaks as much as possible, and keep those methane leaks down, we get a real bang for the buck when we replace coal with natural gas. There's a big controversy about how much methane leaks to the atmosphere. There are other people in the room who know about this. My opinion of the scientific data of what we know right now is that methane losses associated with oil and gas operations will be somewhat higher than the EPA thinks they are, but not high enough to suggest that the greenhouse gas benefits, at least, will be counterbalanced by those methane losses compared to the combustion benefits. That was a really long sentence. I hope that was English. Are the recent earthquakes in Weld County attributable to fracking? I have no idea. I'm done. Thank you very much.